Okay, so we now have the next talk by Professor Vishal Dixit from IIT Bombay. You have already heard from him yesterday. Yesterday he talked more about the physics of convection and the equations and so on. But today I think he's going to talk more about the machine learning part. Yeah, without further ado, I'll open the floor to Vishal.
Yeah, thank you, Adway. Let me at the outset tell you that I am not a machine learning expert, but I am somebody who, as an observer, will try to describe to you what kind of quiet revolution somebody else made. Like somebody must have mentioned this before me. What quiet revolution has happened in two things. One is how is machine learning used to either partially or fully replace convective parameterizations, and also predict rainfall, which is a natural outcome of convection. Okay, so just to jog your memory, what is the goal of convective parameterization? Let's look at that first. I will just write one equation because this is what machine learning algorithms are trying to learn. So phi was our generic parameter. We said it could be either temperature, humidity, or any other variable. Typically, phi is just thought as a function of z. That means convection occurs in a column. That's what we were saying. And the key equation was, so that my model marches forward in time. We just discussed this yesterday, right? I need some tendencies from resolved part of your model, resolved in a climate model. Here, the way model is constructed, the dynamical core, or CFD if you like, CFD part of it will take care of this. And there will be contribution from convection. You can think of AD contribution, which is not resolved. And we said there will be SQs, right? SVs. These typically involve condensation, radiation, yeah. There are a few other processes, mixing, for example, unresolved mixing. The goal of convective parameterization, that's where we stopped, right, is to write this. If it is only ADs, and let's consider again dry atmosphere. And in the dry atmosphere, condensation and radiation are, I mean, radiation, you could think of it as a relaxation term in the dry atmosphere. Condensation is not there. So in the dry atmosphere, it will be mainly writing ADs would be the job of machine learning parameterization. In the moist case, all these things you will have to worry about. And we saw that condensation is a chemical reaction which has its own time scale. Radiation is an instantaneous process. It's an electromagnetic radiation. So whatever your time scale might be, this is happening at the same instant, and every molecule is going to affect every other molecule. This is at molecular level. So just get this kind of, that there is a particular time scale and spatial scale here. There are processes which occur at much faster and much larger spatial scales, which one will have to worry about. Okay, with this, and the goal of convective parameterization is either to replace this or to replace both. Yeah. So with this, I think, background, let's look at, so I'm now going to say, how will I know more information about this, about the subgrid scale, unresolved scale? And I'll keep on saying CRMs, that means cloud resolving models. That means there is another model, much finer in resolution, which has some representation of ADs and condensation and radiation and other processes. So one possibility is you run a higher resolution model and do this. That's what whenever I'll say CRM, it usually would mean that you ran another model. And then you do it in 2D, 3D, we'll do that discussion. Okay, so the goal will be, there are 3 goals for me. One is to summarize recent work on ML parameterizations. Second is, this is only one component of climate model replaced with machine learning, either partially or fully. This is where the whole climate model is replaced with machine learning model. You must have heard this foundation models. I think there's also a talk next week on this. I will tell you things that how I see foundation models from precipitation point of view, rainfall forecasts. We will also do a bit of a discussion about what problems there might be. But I mean, I'm not qualified enough to make deeper comments on foundation models. And then I'll probably show you some results, some ongoing work about how is the skill in one of these models. And if we compare that with physics-based model, what happens? So there are these 3 things. Let's jump into the kind of where machine learning tries to mimic physics-based parameterization. So in this, you have a normal model. You have some physics-based, either empirical or semi-empirical, or structure is learned from physics, but representation of the ODEs that this comes from physics. This is what is currently ongoing. So what you then do is you have outputs of convective parameterizations here. You ask a question, can I just mimic what typical convective parameterization was doing? And the goal was to find out the tendency for temperature, humidity, so that you could march forward in time. So this is what this particular work did in 2018. I think you are not able to see here. You could look up this paper, O'Gorman and Dwyer. They used random forests. And you can already see, so they did some idealized case studies where they just took an aquaplanet model, no real land or orography or any land atmospheric interactions. And they asked, can I just take output of such a convective parameterization, physics-based, and train random forests on that and produce temperature and specific humidity tendency? You can already see that deep convection occurs near the tropics, and the R square between the parent model, the convection scheme from which this was trained, and ML is quite high. You also see that this model is able to produce the depth of atmospheric convection near the tropics being high and gradually decreasing away from the tropics quite satisfactorily. So this happened, I think, 2018. So this was, if you like, one of the first successful experiments of mimicking physics-based parameterization. They use random forests. We will in the next slide see what was the benefit in using random forests. They compared, so this was the relaxed Arakawa-Schubert, which is a mass flux-based scheme. We discussed, right, yesterday, what is mass flux-based scheme, where you try to write these terms as updrafts, downdrafts, how they interact, and so on. So that was the physics-based scheme. And if you compare that with random forest, you get a good kind of comparison. One very interesting thing which has bothered modelers for a long time is, if you were to write precipitation parameterization in a particular way, sometimes negative precipitation is generated. And that has bothered people for a long time. One nice thing that happens is, because prediction of the leaf node is typically the average of target values, the nice thing in random forests is you don't get kind of negative precipitation. That's a kind of added advantage. Which is a tip, kind of, if you were to train, say, neural nets, or you will have to add a special penalty on top to make sure that there is no negative precipitation. Okay. In the same paper, oops. they did something more. They asked, now with this mimicked physical parameterization, can we also reproduce climate change signal? So let's look at this. X-axis is latitude, y-axis is fractional change in zonal time mean precipitation. And they said, if we would to club, so you do simulations either for the current climate or some warm climate, future climate, where you artificially warm surface and look at the atmospheric response. And then you show this data to your random forests and ask a question, can you actually reproduce the fractional change in precipitation per unit Kelvin of warming as a function of latitude? So what you can see is, if it is trained on each climate separately, then you kind of essentially produce the origin parent model's behavior. If you show both the data, that means climate change as well as the current one, then kind of model also performs well. The interesting part happens where you just train on control climate, but expect the random forest to produce climate change behavior. That's where it miserably fails in the tropics. Whereas extratropics is not as bad. Yeah, so you note this, that tropics will come again and again in this series. So tropics needs very careful consideration. So that means in your parent data, the convection scheme couldn't know how to respond in response to for whatever degree of warming that they introduced. Now, if they do the other way, where they train on warm climate, that means they didn't train on control climate, only on warm climate, you can reproduce the response. What does that mean? That means in the warm climate, you had some samples which behave like the tropical response, such that you could just show warm climate and reproduce both control climate and the warm climate. And they kind of systematically showed that because extratropics of warm climate simulation behaves as the tropics of the control climate simulation, you can do this. Yeah. Okay. Let's move on to the next version, where notice the title. Now I have gone away from mimicking the existing physical parameterization, because that will be just as good as the physical parameterization. I showed you yesterday a plot where I myself told you that the current physical parameterizations are quite bad. So if you were to mimic that with random forest, you are going to be at best as bad, right, as physical parameterization. So instead, what Pierre Gentin and others did is they said, I just kind of don't want to mimic physical parameterization. Instead, I will run 2D aquaplanet cloud resolving models at around 4-kilometer resolution. So that means I have a finer scale resolution model here, which is usually too expensive to run for such long time scales as the parent climate model. And I will then coarse grain this data and try to train machine learning on top. They used typical ANNs. And what they show here is C-brain is their model. And again, you will see this convective heating rate, convective moistening rate, T dot, Q dot. And there's a spatial distribution, latitude versus longitude distributions. And you can compare these two plots and see that there are some features which are reproduced. Interestingly, when this was kind of written up, this paper, this much agreement was sufficient. But if you see, if you were to zoom in, if you were to do diff of these two, the difference is quite significant. So if one were to ask a question about a particular region, let's say near the tropics, the forecasts were kind of all over the place. But the nice thing is you could use some neural nets. That's from machine learning point of view. Your simple ANNs, very easy to train. They could kind of give you at least some features of kind of heating and cooling, tendency of temperature and humidity. And this was also one of the first demonstrations of the stable performance of machine learning. Typically, climate drift was observed. What do I mean by climate drift? You replace your physical parameterization with these ANN based physical machine learning parameterization. And if you were to run this model long enough, it produces a different climate than the control climate for which it should be producing. So if that were to happen, that means all these statistics are gone for toss. You would not want that. So although you do get physically meaningful looking patterns, you produce climate drift. Okay, the nice part here was that it was stable performance. This word is important because in all of this, one thing which is very different is the rest of the model is as it is, and you are trying to integrate this online. And most of the time, most of the machine learning papers in climate sciences until now are things on offline. That means you post-process data to learn something. In this case, one part of the model is running its own way in the projections or forecast mode, but you are trying to put in something and is supposed to integrate with the rest of the model online, produce these tendencies. The physical model will do its own dynamical core-based calculation. It will produce new temperature humidity pattern. Machine learning model should again produce tendencies. And this was not achieved before. People were doing kind of offline tests regularly. Okay, let's move on. This particular paper by Ras, Pritchard, and Gentine asked a question about, can we instead of ANNs, can we do things with deep neural nets? And can we still reproduce and produce a kind of integrated seamlessly? So what again they show is, in this case, they replace not only convection, but also radiation tendency. So they ran 2D aquaplanet cloud resolving model. They coarse grained the data. They looked at temperature and humidity profiles. The influence of all of this was then parameterized using deep neural nets. Yeah, so it's not only one convection process, but also radiation and few other processes. Everything as a physics that changes temperature and humidity tendency. What they show here is, for example, this was the control simulation without any high resolution model embedded. This SPCAM is a 2D kind of high resolution model. That means this model also is not the best. You would want a 3D model ideally embedded. But with whatever computation they had, they could only run this 2D model. And this NNCAM is trained on SPCAM. And what you can see is control climate has this double ITCZ, 2 precipitation peaks. And NNCAM kind of reproduces SPCAM. So instead of spending huge amount of computational effort in kind of doing 2D cloud resolving models inside the grid, you could just run NNCAM at much cheaper. But these neural net models also were quite unstable and had climate drift. So instability and climate drift had been a problem in these neural net models. Okay, let's move on and see what others did. This is still 2D aquaplanet. This is the same paper. Like here, we looked at all other, like this was the temperature and humidity tendency, some description of convection. But this does not necessarily guarantee that you also produce the right variability. Right? This is mean. So they compared variability and kind of said that SPCAM, which is a super parameterized 2D cloud resolving model, NNCAM kind of matches that. You can see that overall it does produce tendencies, but it also has a tendency to produce kind of overstate the extreme rainfall. So anything beyond 100 or more is over predicted in neural net based model. Okay, Now let's go to 3D aquaplanet CRM. So this happened with this group, Brenovitz and Bretherton. What? Yes. Yes.
Cam is basically mimic what you are showing is it can mimic the SP cam, right? So that is whatever SP cam can do, the same
Yes.
thing NN cam can do.
Yes.
So I mean, like, so do this. So what is the main argument for this paper? Is it that neural whatever can be done by process-based model or physics-based models can also be done by neural
At
by
keeper
ML
point.
models if they are appropriately trained, or is it like something more? That is, are they claiming any benefits also which these models can offer?
I think the main argument is that it can replace and it is much more flexible. If you were to tune it further, let's say showing it observations, this is likely to be much more flexible than the SPCAM. Also, you could do many more scenarios with DNNs rather than.
So I mean, so are such things discussed also in these works? Or?
Not
Maybe not. No?
Not much. Yeah.
Okay. And
this is like still this field is I think just exploded. I think.
Right. Right.
Yeah.
And what about computational benefits? Like
yes, they do report computational benefits. Many a times it's tens of 10x
orders of magnitude.
Yes, tens of x better. Okay. Yeah. They also report many a times compute effort in training this versus offline performance, online performance. You could look up these papers, especially those who worry about like computation time. Will it be exactly replaceable? They do kind of report this. Okay, so this particular work, Brenovitz and Bretherton, there is a set of papers here. I'm just showing one. Brenovitz and Bretherton said 2D aquaplanet cloud resolving models will not have the 3D structures. There has been some literature that if you were to look at clouds in 2D, you pay a huge penalty. So they said, no, let us do instead 3D aquaplanet cloud resolving model. Use that as the kind of training data set, coarse grain, so that they divided the domain and in training and testing, so that some of these features are kind of represented. But they didn't do notice here, they just did single column model performance. That means this was not embedded in the online model. What they showed was you could essentially produce humidity tendencies well. So truth is the 3D version of the model. This is the parent model, which is a coarse resolution model. You could produce humidity tendencies, but you don't as much produce temperature tendencies. SL in this case is temperature. So parent model is very different than the truth and neural net. So temperature is kind of corrected for a lot more than humidity, if you like. One thing they made note of and is that MSE-based loss function, which was the norm until then, kind of is the main cause of models to diverge. So they wrote a set of papers on this and showed that you could actually go back and do linear stability analysis of the neural networks. Yeah, so they did linear stability analysis of the neural networks and figured out that this particular neural net that they trained, it was unstable to capturing the gravity waves. Usually what happens, the clouds develop, gravity waves migrate at a very fast speed. This neural net, so while this particular training data had such gravity waves, the neural nets were not able to cope up with it. So they were able to find out a physical mechanism of why neural net does not function just by probing neural net systematically and with some classical linear stability data analysis. So I would invite you to look at this. So it's just another kind of way of saying that you might actually train a neural net or ANN or DNN, but offline performance does not guarantee that it will work online, even in the single column models tests. Okay, let's move on. Let's look at somebody who found a stable. So until now, I've been telling you that people use neural nets. Things were not, things were not able to, they were not converging. or there was a climate drift. What this work by Yuval and O'Gorman, this I think appeared in Nature, I think Nature Communications, it showed is if you were to again train from 3D cloud resolving model, so this is your low resolution control kind of model. This is the 3D cloud resolving model. If you were to again do similar exercise, you could essentially reproduce this with random forest based convective parameterization. There are two other things that they mentioned, which are, I think, worth noting, is that random forests as a kind of side benefit give you two other things. One, it avoids divergence, and it also avoids climate drift, because although you don't enforce this as a loss function in any way, you random forests just by their nature actually conserve energy. So if you conserve energy, then likely possibilities for climate drift are less. So that's a one benefit. What they also showed is if you were to compare statistic of mean precipitation in high resolution model, low resolution ML based parameterization or parent climate model, you typically have a single ITCZ in the parent model. The machine learning based random forest based algorithm was able to reproduce the two precipitation peak, something that your high resolution model produces. It also produces the extreme precipitation with some faith. You must notice that everywhere here the truth is the cloud resolving model, which in itself is a model output. Yeah. Okay. Let's look at the next study. This particular paper by Giles, it came last year. They said that until now you had been either mimicking physics-based convective parameterization, or you were using either 2D cloud resolving model or 3D cloud resolving model. Let us go away from this type of a thinking. Let us now instead run 3D cloud resolving model, generate some statistical understanding of how temperature and humidity and its tendencies, how do they look? What does the statistic look? What does the distributions look? The joint distribution of temperature and humidity and their tendencies. And then instead train a parameterization which has the goal of producing tendencies purely as a Gaussian process. So multi-output Gaussian process because you have these two or more variables. So you look at the joint distributions and try to learn the Q dot, the del T of Q or del T of capital T as a Gaussian process. So this is purely, I mean, the background distributions come from physics-based model, but the process in itself doesn't care much for spatiotemporal evolution of convection. It's just a statistical model, if you like, embedded. What they claimed was there's some improvement in precipitation distribution. So this is the parent model. This is modified model. You can see that the error, which was much more blue in the tropics, became less blue. And in the exatropics, there was some significant improvement. One caveat here, although, is that such ML parameterizations, which are just purely statistics based, they run the risk of producing unphysical states. So you could use maybe this to look at the future climates possible, but it may not kind of work in the forecasting point of view, weather forecasts. Okay. So this is really kind of fresh from the oven. This is Hu et al. 2025. The manuscript is on archives, is yet undergoing the review process. What they said was, until now, everybody has either mimicked convection parameterizations, either 2D or 3D aquaplanet simulations, or used purely statistics-based replacement of parameterization. Why don't we go to the real world? So that means you would also have land. you would have mountains, you would have land atmospheric interactions because of the Daniel cycle, soil properties. I think many before me have told how complex the system is. Why don't we say that? Why don't we run a 2D cloud resolving model, which partially cares for, ideal would be the 3D real world CRM, assuming that's the truth you would want to nudge to. What they show, I think, until now is they use a different kind of architecture now, unit plus perceptron. They show that you can have a stable performance. Again, the story is it does mimic the parent 2D real world CRM. Notice that the largest precipitation errors are always in the tropics. You would have noticed this. In every plot that I showed you, largest precipitation errors are in the tropics. Okay, so let's move on and ask, until now people have done, so one of the case was real world CRM. Some people said, no, let's go back to aqua planets. Let's not bring in land. Instead, let's look at the 3D aqua planet cloud resolving models as the truth. But we know a particular property of convection that typically as the resolution in the climate models go lower and lower, you cannot fit one particular cloud cluster or a mesoscale system, typically 100 kilometer, 200 kilometer. You cannot fit that in just one grid. That means as the grids become smaller, 2 or 3 adjacent grids will actually have the structure of the whole system. In our typical thinking, convection scheme always does vertical mixing, just up and down. It doesn't care for the 3D structure. They said, why not? Let's instead of doing only a column-based learning, let's look at all the adjacent columns, because the organization happens on a much larger length scale and there are structures you would want to learn. This is, I think, still under review. What they seem to show is, if you were to just take this and along with this provide some vertical velocity in the column, so that is NN1D plus W, and NN3D is where you give the 3D kind of data every time, but you do not give the vertical velocity. And you compare this NN3D and NN1D plus W, you'll see that NN1D plus W actually wins. So this paper does not make a comment about why that happens, but it appears that knowing the vertical velocity in the column has as a predictor, much more potency than maybe having some special structure in the organization. Okay, this is also kind of the first algorithm which considers the 3D structure. People have been saying this for some time, that maybe your cloud, sometimes they are tilted. If they are in your adjacent grid, they might rain actually in the grid next to the grid from which they originated. And models have not been kind of worrying about this. This type of thinking allows you to think like this. Also notice that the same group which was previously using random forests have now migrated to neural networks. I think this also, I couldn't find a particular reason that they gave in the paper, but something for machine learning experts to think about as to they migrated away from random forests and brought in neural networks. Okay. So this is like a summary about what all people have done. You'll see very few have actually done prognostic, very few. So it's still in the developing phase. Let's move on to the second part, where I'm going to show you 3 different models, which you will hear about foundation models. I am going to talk about one called neural GCM. Maybe Professor Goswami may have mentioned this. This, from the modeling point of view, is a one step forward because of what they did here. You have your forcings and inputs. What we knew all the while was the learned physics, which involves condensation, radiation, and so on, where a lot of semi-empirical or empirical or our thought models, cloud models, they all were coded. that was the main place for origin of errors. I'm sure Professor Goswami must have mentioned this. Growth of errors from convective parameterizations. So they segregated this from the dynamical core. And the second thing they did was, the way dynamical core was typically written in Fortran didn't allow you to do any back propagation. So they essentially rewrote the dynamical core and made it kind of fully differentiable. So if you know something has gone bad, you could actually back propagate. That was kind of one great achievement. So this model then can, given the initial conditions, can kind of march forward, use that as the initial condition and keep on marching forward. And the claim is that this could either do a short or medium range forecast, or you could also run it as a climate model. That means you run it for a long time and then worry about the statistic of climate variables. Okay, what did they learn? If you look at the tropical precipitation minus evaporation distribution and compare it against the ERA 5 data, now you will see, I'll change my kind of terminology. I've been telling you the training data came from either 2D CRM, 3D CRM, one of those, or physics-based parameterization that things machine learning algorithm was trying to mimic. Now the standard is ERA 5 data. This is a reanalysis product. What you can already see is in tropics, the ERA 5 data has much higher precipitation. So neural GCM kind of under predicts precipitation anything beyond 25 millimeter, which is quite usual precipitation. It's not only the extremes, but even the mean precipitation is under predicted in this particular model. Whereas in the extratropics, you will see that it essentially captures ERA 5 performance. You can see this plot in the spatial structure. Most of the rainfall errors come from the tropics. So although this model is a great achievement, I think for tropics, it's still not a good news. For us, for most of the tropics, precipitation is much more of a key variable than temperature. So you may achieve great performance in temperature, but if precipitation is not captured well, precipitation through phase change also percolates into your ability to predict temperature because of the feedback between these variables. That's not as much so for extratropics. Okay, so let's look at one more model, which is called forecast-net, which is based on Fourier operators. So what is shown here is the initial condition, and two insets show initial conditions in this box, that box. At lead time of 36 hours, forecast-net produces these two pictures, and it kind of matches to your eyes quite well. The thing, I mean, let me also tell you my view of this. I would have liked difference of this minus that, and with proper scaling, and then I would say, yes, this has skill. So you can see that it has some spatial structure, but intensity is not good. If you were to squint, look at again tropics, you will see that the small scale structures in precipitation are hardly produced. One nice thing in this particular, again, foundation model is that it is based on Fourier operators. So you have gone away from grid-based training and have instead asked, can I actually do a Fourier transform of whatever data I'm given and do training on in the Fourier space, frequency space? If I were to do that, you essentially want to learn the function that is giving such a data on grid. So if you learn function, by implication, you would think that it would be hopefully continuous, differentiable, and so on. So you could essentially have, in the real world, I mean, in the ideal world, have infinite ability to zoom in. That's quite special. So that means you could produce such image at finer and finer scale. Okay, I think I'll probably not discuss. There are a few other models which you will hear next week. I think there's some discussion going to be there on Prithvi, I guess, also on maybe Pangu weather. I can see that will happen next week. Okay. So that will happen so you will hear from experts in that, those who probably have taken part in development. Uh, Let me instead tell you this particular website called Weather Bench. I would highly invite you to look at this in some detail. Weather Bench compares ML-based rainfall forecasts from many models. So some of these models are ML kind of hybrid models. There is IFS, which is considered arguably the best forecast model developed by ECMWF, European Center. This IFS ENS is the multi-ensemble mean from that, and it kind of gives you comparison. ERA 5 dataset, for example, is produced from one of the old versions of IFS. What you see, I think first thing I would like you to notice is that typically most models give you 2-meter temperature, surface pressure, 10-meter wind speed, and a few other climate variables. Very few actually give you precipitation, which really matters in the tropics. So the key models are Gencast, maybe Fushi, and there's also, I think, nowadays there are some updates on this. For example, ForecastNet also gives precipitation forecast as we saw, but is not participating in this. So here, the darker the red, it's kind of worse on one side versus the other. You will see that Gencast is doing, I think, not as bad. And this thing was done for 2020, but they keep on updating this. So I won't be surprised if there is Weather Bench next version where they do it for every day and then post this. This is quite fascinating effort Google has done, Google research. Okay, with this, I will again kind of stop for a while before moving on to telling you something about extreme rainfall events. So if you have any questions, I am happy to take them now on this. But if there are no questions, I could move forward and we could go for lunch quickly. Okay, so I think until now, I have been telling you that people have either tried to replace convective parameterizations with whatever they did, or people have tried to totally train models, replace climate models themselves, train them with some machine learning. But one thing I would like to kind of show you, this is the slide I showed yesterday. And I was very much critical on traditional convective parameterizations. I told that 25 CMIP models kind of give you large precipitation errors, or super parameterize these 2D cloud resolving models, they have large error. Global cloud resolving models, that means it's a 3D cloud resolving model, which typically has a resolution of 1 kilometer. That means it resolves a cloud cluster typically of the size of 10 kilometer. They have large error. Even ERA 5 reanalysis has large error. My point of showing this slide again is to tell you that for most of what I said before, ERA 5 data was the benchmark for foundation models. So that means all those models can be at max as good as this much error. This is precipitation. This is annual mean global kind of precipitation. Yeah. Yes. Yes. And annual mean precipitation. So they are as good as only this. The data on which some of these cloud resolving models were trained on also has a bias in precipitation. So they could be as good as this or that. And then are traditional parameterizations are they doing really bad as compared to any of them? I think the jury is out. My take is that this is much more flexible. So if you were to have a machine learning based parameterization, you could do many further things cheaply. So you could either tweak it, show it, say real observations. So in this case, comparison was done with GPCP rainfall data. You would notice that in any of my previous plot, I didn't utter a word observation, right? So I think all these models will have to ultimately be compared against some observation and then retuned back. That's my take of this. Yes. It's still not the statistic of, fair enough. Yes. Yes. Yeah. Yes. They come from different ways of how. Yes, yes, agreed, agreed. We should probably call this still an error, and maybe more analysis of the full distribution could tell us if it's systematic or not, or if you need more regional tweaking or what. Agreed. So I think my comment on this is most foundation models do not compare rainfall distributions with or forecast with precipitation observations. This we should do. Okay. So with that, maybe let me spend, how much time do I have? 7, 8 minutes? 5 minutes? 5 minutes. Okay. In next 5 minutes, let me tell you this work led by students. We were saying ultimately these companies which have developed these foundation models, they will make it available to us. They have tuned it. One thing would be to care about kind of developing a new model on its own. If you look at these papers, this effort is tens of thousands of GPU core hours on something like A100 or H100 GPU, which is practically impossible at the scale of any university, one university. So we were saying instead what we care for is the extreme rainfall events, and most of the either replaced convective parameterizations or foundational models, they are mainly trying to get the global patterns right. And most of the statistic was, I mean, to get the statistic right. Instead, can we actually run a physics-based model and produce a data set only for extreme weather, so that if you have this data set, you could supplement whatever was trained before by any of the previous efforts, could supplement it and tune it to get extremes right. That was the idea. So I'll show you two types. One is the efforts we made on by running physics-based model. Use physics-based model as the data generator, if you like. That's what we tried. So I think I have 5 minutes. I'll quickly directly go to the yeah. So I think what we did was we set some criteria, picked few celebrated extreme rainfall events. Some of you may have experienced them. For example, I was caught up in this Mumbai 2005 extreme rainfall event myself. We ran WRF simulations with this choice of parameterizations and schemes at 1 kilometer, 3 kilometer, 9 kilometer, and 27 kilometer. For innermost two domains, we put convection, this deep convection scheme off. That means I have already resolved some part of the ADs, right? Like CRMs. And in the larger domains, I kept convection scheme on. Then I have this library of data sets. Then we did some kind of looked at how good are they. One typical question any forecaster will ask you is, you say so much about going to cloud resolving models. Are they going to improve forecasts? I'll try to kind of say my take on this. So I think again, in the interest of time, yeah, you could just take a look at this animation, which is working thankfully. How bad? So more the red and blue color here is that means WRF was quite bad as compared to either satellite-based product or IMD product, which is 1 kilometer and 10 kilometer resolution, 1 degree or 10 kilometer resolution. So you will see that there is a varying skill in capturing this. This slide is busy. I just want you to notice that if you were to compare over the whole large domain and compare the typical scores, so if you have many more false positives, then your FAR score is more. And if you have probably, if you miss many of the rainy events, then your POM is more. So what you can see is, when compared to iMerge, the largest domain is performing average for in terms of FAR, average in terms of form. But when you compare it with IMD, it's quite poor. So that means the data set against which you compare extreme rainfall itself matters. Yeah, and you will see this being happened. So this A to I is all these different events. And then if you were to compare across medium domain, uh, essentially it's a similar effect, telling you that either if you were to look at in the vicinity of extreme rainfall event or farther away in a much bigger domain, what matters much more is, I think, so WARF has some skill with respect to iMerge, but has almost no skill with respect to IMD. IMD is 25 kilometer, yes, yes. Is 10 kilometer, yes, yes, yes. Yes, yes, everything is brought to the same one and then compared. Then what you could do is, there is this larger domain. You could only take the chunk of large domain, which is comparable with the smaller domain, and do the kind of comparison. Again, I don't want to kind of spend more time saying that again, you could also look at probability of hits or few other skill scores. What you can see is that this particular analysis tells you how good is the spatial distribution of rainfall. The grid in which it was supposed to rain, was it raining there? And if yes, so it's about spatial distribution. We will also look at the quantitative intensity kind of based evaluation. So my take here is the precipitation observations have either coarse resolution and are interpolated. So that means if you care for reproducing extremes, what you use as truth itself will have some influence of interpolation or the inversion method that is used. So there's a poster Shreyas is presenting to partially address this. Can you have a data set which which kind of merges the advantages of IMD's ability to represent the ground truth rain gauges and iMerge's ability to get the right spatial footprint? Yeah, that's an advertisement for Shreyas's poster. Let's look at what happens in terms of the intensity. So spatial pattern, WARF has some skill with respect to iMerge, which has good spatial distribution, right? IMD does not have as good a spatial representation. If you look at coarse resolution, that means this is typically NWP scale. 27 kilometer and 9 kilometer, what I'm showing on x-axis is iMerge precipitation, on y-axis WARF precipitation. And we have divided we are kind of comparing it quantile by quantile. So asking a question at this particular intensity, whatever quantile was there, how good was it in WARF? X equal to line is the dotted one. So you can see that at coarse resolution, in most of these cases, this is already a few terabytes of data. Most of these cases, there is an under prediction. So with convection scheme simulations are in some sense not able to produce any precipitation value beyond 150 millimeter. Whereas if you go to say 3 kilometer or 1 kilometer, there is a better match with x equal to y. But more importantly, there is a good representation of, as you go to higher resolution, your model can produce atmospheric states which lead to extreme rainfall events, 150 millimeter or more, which was totally missing. So this was, if you were to train your machine learning on any of these schemes, it just doesn't know what such a state looks like. Whereas here, you could have such states available to you. Yeah, okay. So, in kind of favor of xWeatherLib, I think I want you to think of it as data set representing physically consistent atmospheric states. So it has ability to produce extreme rainfall. So think of more of it like it has a more complete representation of rainfall atmospheric states. And that means high resolution model on its own may not produce a better forecast. That means given initial condition, it may not have the right temporal sequence of precipitation, but it does have ability to produce atmospheric states which lead to extreme rain. So you could then use this as a data, parent data, to train further models. This is ongoing work. I think I have already spent 5 minutes. I have one more slide to flash. Then we asked this question on GenCast. So the previous one was physics-based model. We asked this, can GenCast produce the same extreme rainfall events? I'll just show you two of them. In one case, we asked the same question we asked for the physics-based model. At the lead of 4 days, can you produce the right quantile for this Mumbai case? You can see that GenCast has a better match as for which ERA 5 was the training data for this. But if you were to compare with iMerge, it's quite poor. At 12-day forecast, it hardly produces any rain beyond 80 millimeter, whereas it should have been producing much higher rainfall. Typically, around 900 millimeter rain happened on that day. Okay, another case which was outside the training test. So this was 2005, which was part of the GenCast kind of training data set, but an extreme sample out of it. The next one is outside training set, so unseen data and extreme. And you can see that this particular case was, at least in terms of quantile, was captured at 4-day as well as at 12-day. Not showing many such cases, just kind of giving you some idea about GenCast does have a skill in getting few even at the lead of 12 days. Why did it get it right is the right question to ask after this, which we haven't yet asked in GenCast. Okay, what we then tried asking is what the same question we asked you yesterday. Can we take these bad forecasts and train them into observations? And this is where we didn't ask this question on the extremes per se, but in general for the full distribution of precipitation. So we ran GenCast for the whole of JJ's 2018, the same data set we gave you. And this is, I think, credit to Pratham. He's kind of trained a Cornwall team. Our thinking was maybe there is a special pattern that justifies usage of convolution. And there is some temporal memory. So you could use Cornwall STMs then. Can Cornwall STM basically take bad forecast and turn it into a better forecast model? And for that, our reference was iMerge. This is my last slide. What I would like you to focus on is the GenCast error, RMSE, was this much. We tried several either ways of scaling the data, and you can see that visually they all appear similar. It is only when you do the difference between no scaling, one way of doing it with different batch size and so on, with GenCast that you see that GenCast essentially fixes kind of rainfall by a couple of millimeters. By no means this is the kind of end of tuning or anything like that. But I think improvement of couple of millimeters for my liking is not sufficient when you have around 8 or 9 millimeters to fix on an average. It's like only 20% improvement. But when I see some literature in terms of what improvement people report, it looks like 20% is also reported. Although I should tell you with caveat that this is only 20% fixing of the error in general. But I think such kind of approaches can be taken. Let me revise what we discussed. There are only 3 take-home messages. That it's still few years before which a fully stable, online, fully ML-driven parameterization is made available, or you develop it. The second part said we looked at ML foundation models. I think we will have to focus on representation of tropical precipitation. So most models are reported in a way that they show statistics for few climate variables except precipitation. And especially tropical precipitation is quite bad. We will have to fix it. And the third one is, I think we should probably as a community contribute to X-WeatherLib more and more. What we did was a small effort to actually have this out-of-sample data for out-of-sample cases such that it could be used to train further models. With that, I'll stop. Thanks. Sorry, Adway, I think I went 5 past.
People may be in a rush to learn off the cafeteria, but if any curious guy is, if the curiosity is overpowering the hunger, you may squeeze in one quick question. No? Okay, people are too hungry.
Sure.
So let me frustrate them by asking this one small question. So, like you mentioned, physically consistent atmospheric states. So, I mean, what are the some physical inconsistencies that are observed right now, which you need to be
So, for example, in the humidity and temperature space, you are kind of, for example, one of the examples I think I gave was this. They have, let's go back to this particular slide, where they trained things on just, yeah, this one. So in this, you don't care for if lower tropospheric moistening leads to convection or not. Moistening could be anywhere, you could still accept it as a kind of acceptable solution. But in such an approach, you would just see if the joint distribution allows for it and what is the probability of that. Whereas if you were to kind of take data from a physics respecting CRM, you would then not make such errors which we know based on our understanding of buoyancy and convection are physically implausible. Okay, yeah, thanks. Thanks, Adway.
thank the speaker.